Now let's see what do we mean by convergence of a sequence. So before that, can you all remember that in calculus 1 we discussed the limit of a function? Say for example, if we have a function like this, and at this point, let's say this point is equal to 5, and if we have the function like this, let's name the x coordinate as 2, and the value of the function, let's say 7. So if this is the graph of our function, then that means the value of the function at 2 is equal to 7, but the limit of the function when x goes to 2 is equal to 5. So what do we mean by this limit? Or I mean, what is the idea that we can take by looking at this formula, that limit of fx is equal to 5 when x goes to 2? That means the value of the function fx when x goes to 2 seems like it is approaching 5. So the value of the function at 2 need not to be equal to 5, but it looks like the function values approaches 5 when x goes to 2 from both sides, right? So that's the basic idea of a limit. And how about this one? Limit of the function when x goes to infinity. Say for example, if we have a function defined as let's take this one. So what do we mean by the limit of fx when x goes to infinity? How do we calculate the limit? We just since this is the infinity, we take the highest power out, so this becomes 1 over 1 plus 1 over x, and when x goes to infinity, this goes to 1, right? So that means this function looks like it goes to 1 when x takes a very large positive number. That means if we have 1 like this, when x goes to a very large number, the function values should asymptote with 1, right? So it's like the function looks like that it approaches 1 when x takes very large numbers, right? And now all these things are defined for functions, right? And remember, in the very first video I mentioned we can always consider a sequence also as a function. But the thing is, now see here in this function, our domain was all the x values. Let's take from 0 to positive x values. It's like we can take each and every real number in this real axis as the inputs for this function, right? But if we define a sequence with the same formula, what happens is we restrict our choice for the value of the domain, right? So then we restrict only the values, like we restrict only the natural numbers, right? So if we can have the same equation but only with natural numbers, we can write the formula like this, or in a more suitable way we can write the formula like this. And for the sake of completion, we can even mention the starting point and the end point. So this becomes a sequence. It is also a function, but we rather prefer to call it as a sequence. sequence, right? So the only difference is that for this one we only choose the natural numbers from the set of real numbers. Starting from 1 it goes up to infinity. And again the limit of the function, so I write an instead of writing it as fn, and here like in the original case it was like this, right? Limit of x of fx when x goes to infinity. But here what we do is we consider the same situation, but we have some slight change of notations, right? See here, instead of x we write n, because we are in a sequence, and sequence we specifically mention simple n for the domain values, right? So here we say n goes to infinity. What will happen to the sequence when n goes to infinity? That means what will happen to this term when n goes to infinity? And you just have to do the same calculation as before, right? So here we can take n out from both sides, and you just have to do the same calculation as you did for the normal function in here, right? But the only difference is that we are considering a sequence, right? So anyway, from this result, that means the limit of an when n goes to infinity is equal to 1. So from this result, once again we can say that the sequence points, so these are some discrete points. In other words, if we list down these points, it will be like this. Starting from 1, it will be 2. The first position will take 1 over 2, and the second position will be 2 over 3, and then 3 over 4, 4 over 5, right? So likewise, when it takes larger n values, it will be very close to positive 1. So you have the same idea as it was for the normal function, but there are some slight changes of the notation. That's all, right? Other than that, it has the same meaning as the limit of a function when x goes to infinity. But here, instead of writing the function as f, we write an, and instead of x goes to infinity, we write n goes to infinity. But the idea is more or less the same, right? So the idea means when you list down the terms of this sequence, towards the end it looks like that the value approaches 1. So when you move towards the right corner, the numbers will be very close to this limiting value, which is in this case equal to 1. So what we have to do is we should be able to calculate the limits of some given sequences. That's all. But the idea is like you are just calculating the limit of a certain function, right? And here we have a special situation where you are choosing some discrete values as the domain of that function. And other than that, everything is the same, right? It's the same thing that you did for calculus 1. But in calculus 1, you just did it for a general function, and here in our course, we are dealing with sequences. So from here onwards, I'm not going to compare sequences with a function all the time, right? So I'll just mention it as the limit of the sequence. So I'm not going to remind all the time that this is also a function, right? So we are just dealing with the sequence concept, right? So here we are considering the limit of this sequence, and if the sequence is defined like this, we just find the limit in the very similar manner as we did in here, right? So, and that means our first target or the first skill that you should have is to compute the limit of any given sequence. And finally, we have a term called convergence of a sequence. That means if a sequence converges, that means the limit of, if the limit of this sequence take a finite value, we say that the sequence converges, and if it is infinity, we say the sequence diverges. For example, if we consider our usual sequence, which is this one, we saw that the limit of this sequence when n goes to infinity was equal to 1. But let's say this one, let's define our sequence like this. That means if we use the correct or the appropriate terms, we can write it like this, or in other words, we can write it like this. Okay, you don't have to mention a all the time. You can just use these curly brackets for the right hand side of this equation also, right? So for this sequence, you can see that when you take the limit, it will go to infinity, right? So this will go to infinity. In other words, like if we list down the terms for this sequence, it will start from 1 and go like this, right? So you can clearly see that when you move towards right, the values will increase very largely, right? So simply that means the limit of this sequence is equal to infinity. That means we for this one we have the limit as infinity. So if the limit is infinity, we say that the sequence diverges. And if the limit is finite, we say that the sequence converges. Okay, right. And in the next videos, we will go over some useful theorems that will support this convergence of sequence.